Hey, welcome everyone. I thought about this a little bit over the last couple of days, how I'm going to make this go the best. And I think the idea is I'm just going to run through it, and I talked about this yesterday, I'm just going to run through the whole thing, and I'm going to offer little mini lessons along the way. So, for example, I'll put problem one, say, okay, here's what you're going to look for on this one. A quick mini lesson on limits as far as equations are concerned, and just go right on through this, just so we can start to put things together, and maybe you can get most of the questions then on your own. But I think that's probably the most important thing, is that you actually work. And watching me is going to get you so far, it's not going to help you learn it all that well. You're much better off sitting with your review guide and your pencil and your review paper and your review guide answers, and working through as much of this as you possibly can. And I'll probably mention this a couple of times as we move through the next couple of days, but that's what that's what studies show. The more work you put in, the better off you're going to be. And math in particular, it's more time you spend working problems. It's not watching other people work problems, it's actually working problems. That's when you tend to do the best. Without further ado, then, let me start in on the first page. We'll see if we can get the first 3 pages done today, with maybe not all the answers done, but at least giving you an idea where we're going to go on this one. Let's take a look at problem number 1, maybe parts B, C, and D. A, the limit as x approaches 3. Maybe I'll do that one as well. So I guess we'll start there. So its limit as x approaches 3. There is x equal to 3, approaching both from the left and from the right. Doesn't matter which way we approach. As x gets closer and closer to 3, the y value gets closer and closer to -1. So again, we're looking for the limit is what's the y value as x gets closer and closer to a value. In that case, it was the value 3. Now we're going to approach -1, and we've got a lot going on as we approach -1. Solid dot there, open circle there, and now I'm going to go from part B. We're approaching -1 from the plus sign, that means from the right. As we move closer and closer right on the function, as we move closer to the right, the y value that we're getting closer and closer to would be -1. So the limit, so the answer to B will be -1. As I put my pencil someplace on the function where x is less than -1, I'd be over here, and I follow that, I get closer and closer to x equal -1 here. I notice that the y value is getting closer and closer to 0. And since these two, so there's the answer to B, there's the answer to C, and since those two aren't the same, then the limit as x approaches -1 does not exist. Counterpoint this one, as we approach 3, both from the left and from the right, the y value is getting closer and closer to -1. Question E, is the function continuous at 4? 4, let's see. Yeah, here we go. Yeah, it is continuous at 4, and the reason it's continuous at 4 is because the limit as x approaches 4 of f of x, so it doesn't matter if we approach from the left or from the right, that number is equal to a +1, and also that happens to be the value of f of 4. So the y value is exactly what we were expecting it to be as we moved along. If I could offer a counterpoint to that, let's say we had a function, and that isn't this function, but let's say we had a function that had, say, an open circle there and maybe a point right there. We'll call that, for the sake of argument, let's say that that value is at -3. If I take the limit as x approaches -3 of f of x for this one, both from the left and from the right, that would have been a -1. F of -3, however, that's that point right there, that's equal to 0. And since those two things disagree, since the limit is not equal to the f value at -3, that would not be continuous. So this function has a bunch of discontinuities. Discontinuities are places where you, if you're going to draw the graph left to right or right to left, you'd have to stop, pick up your pen, and before you moved on. So let's see, on the graph that we have, again, not this one here that I just drew on, but the places where this is discontinuous or at -1, it's discontinuous at 1, it was discontinuous, if you look at the, let's see, I had that little funky thing come down here, it's discontinuous at 2, there's a big jump at 2, and that's it. So it's discontinuous at -1, 1, and 2. Is a function continuous at 2? No, it's not. And the reason it's not is because the limit as x approaches 2 of f of x does not exist, and that's definitely not equal to f of 2. F of 2 is equal to 1. This one does not exist. Problem 2, base your limit on the graph. The limit as x approaches 3. Okay. Well, again, I'm going to approach this one just as I did in the first problem. As I get closer and closer to 3, what y value is the function getting closer and closer to? Then we'll approach both from the left and from the right. So here's my graph on problem number 2. Got an asymptote over here 2 units away, and then I have a graph that looks like that. So as x approaches 3, both from the left and from the right, the y value I get closer and closer to is a y value of 2. Okay, what's the y value? Yeah, what's the y value as x approaches 2 from the right? So now we're on part B. Here I'm at x equal 3. Here I'm at 2.5. As I get closer and closer to x equal 2, the y value looks like it's going through the roof. So that would be infinity. What's the limit as x approaches 2 from the left? We'll have to look at this other branch to figure that out. Again, there's x equal 2. Here's x equal 1. Here's 1.5. As I move this along this graph, getting closer and closer to x equal 2, the y value goes to negative infinity. And then finally, what's the limit as x goes to negative infinity? So if I were to let my x value, here's x0, -1, -2, -3, as I let x get further and further to the left, the y value that I'm getting closer and closer to is the value of 1. So those are the graphs and the limits, and they go fairly smoothly, I think, for most students on the final. There's maybe a little difficulty with the idea of a limit, and there will be that precise definition of a limit on the final. At least there always has been. All right, on to problem 3. Now in problem 3, we're talking about limits, and there's 3 kinds of things we're going to look at. If we have a limit as x approaches some number, or if we have a limit as x goes to infinity. If we have x going to a number, there's about 3 things that can happen. We get a 0 over 0, in which case we factor and cancel. Okay, there's case 1. Case 2, we get some number. In that case, we celebrate, we're done. Case 3, we get some number over something that approaches 0. Okay, that's the case we're going to look at last here. So factor and cancel, if you get a 0 over 0, if you just get some number, that number is the answer, and then a number over 0, we have a couple of options there. So I'm going to do those problems first, and I'll come back to the limit as x approaches infinity later. So problem number 1. How about problem letter A? Problem 3A. So I plug in x equal 4. I notice the top is 0. And if I plug in 4 at the bottom, I get 80 minus 72 minus 8. I get 0 as well. So the very first one is 0 over 0 as I plug in x equal 4. That tells me that x minus 4 must be a factor in both the numerator and the denominator, since those are polynomials. I'm going to factor those. Numerator is simple, it's 3 times x minus 4. The denominator isn't that much more difficult because we already know what one of the 2 factors is. Now remember, the denominator was 5x squared minus 18x minus 8. So I know that this lead term has to be a 5x. That's the only way when I FOIL them together I'll get the 5x squared. I know the trail term at the end must be a plus 2. That's the only way I can get the negative 8 at the end. And if you do FOIL those out, and you probably should if you get one of these on the test, you'll recognize that that is what we started with. So now I have the limit as x approaches 4. The only thing that's different from this, from what I had in the beginning, with this from what I had in the beginning, is now it's in factored form. If you get 0 over 0, you can always factor. You should know what the factor is. Cancel that factor out and now plug in 4. What is that? 3 over 22. Okay. Part B, limit as x approaches negative 3. I'm going to plug negative 3 in there. I get negative 2 in the numerator, negative 3 in the denominator, 1 minus 9, negative 9 is 10, negative 1/5. We got a number. Done. Okay. I'm going to move to problem D and then come back to problem C. So we have the limit as h approaches 0. This is starting to look like our definition of a derivative. Negative 2xh plus 3h minus 5h squared. So if I plug in h equals 0 first, I get 0 plus 0 minus 0 over 0, 0 over 0. That's the case where I should factor and cancel. I should recognize now that h equaling 0 gives me the problem with the 0 over 0. So there's an h that you can factor out of both top and bottom. If you factor the h out first, you get that. There's another technique that we developed back in the algebra section. If you have a common factor in every single term, you could cancel it directly. So it doesn't matter how you do that, but sooner or later that h is going to disappear. Now we plug in h equals 0 and we wind up with what's left over, minus 2x plus 3. Oh, by the way, if you have questions on any of these as I'm working through them and you want a little more clarification, send me up a little chat note and I'll go through it in a little more detail. Okay, now back to part C. Part C, we have the limit as x approaches 5 from the left of negative 2x over x minus 5. Now, if I plug in a 5 here, both the top and the bottom, I get a negative 10 over 0. And that tells me that this answer has to either be a positive infinity or a negative infinity. I'm taking a number and dividing it by something that gets closer and closer to 0. There are a couple of ways you can do this. Maybe a chart would be handy. We're going to let x approach 5 from the left, so numbers that are less than 5. If you wanted to make a chart just to see how these go, you could. There's x minus 2x over x minus 5. I remember we struggled a little bit with our chart making on this one, so let's make sure we can do this chart right. I'm going to start 1 unit away from 5. I'm going to start at 4. Then I'm going to move 1/10 of a unit away, 4.9, and then 100th of a unit away, 4.99, and so forth and so on, if you'd like to put a few more in there. So I'm going to do my best to figure these out mentally. This is negative 8 over a negative 1, that's 8. This would be negative 9.8 over negative 0.1, that's 98. This would be negative 9.98 over negative 0.01, that's 998. If I went one more down the list, it would be 9,998, and I can see, therefore, that those numbers keep growing really by a little factor of 10, a little more than 10 each time, so those are definitely going to infinity. All right, then the next ones we have our limits as x go to infinity. So we're considering on the graph what happens clear over there as x goes to infinity. Like that one graph I had on problem 2, the function got closer and closer to y value of 1 as x went to infinity. So that's sort of the idea we're looking at on the next two. Where are they going to go to? And again, if you want to, you can make a list and sort of see where these things are going. Or there's rules that you can remember. So let's maybe start with the list and then I'll come back and get the rules. So negative 2x over x minus 5. Oh, it's the same function, isn't it? So x minus 2x over x minus 5. We're going to send x to infinity. So don't start here at 1. We want big numbers. So let's start at maybe 1,000. And then 10,000. And then, I don't know. We started at 1,000. Let's go 1,000. And then maybe 1,000,000. And see where that takes us. So if we plug 1,000 in there, it'll be negative 2,000 over 998. That's really close to a negative 2. I can tell that already. But I'm going to plug in the calculator and see how many decimals I have before it varies off. So 2,000. Negative 2.004008. Now I'm going to plug in, I guess, 1,000,000. I need an extra 0 there. So I plug 1,000,000. This will be negative 2,000,000 over 999,998. Man, that's going to be so close to negative 2. But I'll calculate out. Yeah. Negative 2.00. How many zeros are there? 1, 2, 3, 4, 5, 6. So this is really close to negative 2. This is even closer to negative 2. That's going to negative 2. So that's sort of the chart way of doing it. The other way is to look at this fraction and ask yourself which has the higher degree, the numerator or the denominator. Well, in this case, they have the same degree. So my answer here is going to be the ratio of the lead coefficients. This is minus 2 for the lead coefficient. The highest power is x. The lead coefficient is 2. The highest power here is x. The lead coefficient there is 1. So if you have a situation where you have sending x to an infinity or negative infinity with a rational function, all you have to do is look at the interplay of the powers. Now, we looked at 3 cases. There's only going to be 2 cases to worry about on the final exam. So here's the other case. What's the limit as x approaches infinity of the next one? 3x squared plus 16x minus 12 over x cubed plus 5x squared plus 36. Again, we're setting x to infinity. So I sort of walled off. It worked out really nice here on this exam sheet. The first 4 had x going to a specific value. The next 2 on the next column carried over to a separate idea. What happens as x goes to infinity? If you remember back, this one has a lesser degree. This is of degree 2. This has a higher degree. The highest power there is the highest known as 3. This is degree 3. And if this power is bigger than this one, the denominator is going to get bigger faster than the numerator. This fraction will go to 0. So I'm going to put in just a few values, and I'm just going to round them a little bit. I'm going to plug in x equal to, I think I'll start with 1,000, and then I'll go x equal to 10,000, and then I'll go x equal to 100,000, and show you how these things approximately are going to go. If I put 1,000 in here, this will be virtually, not exactly, but this will be virtually 3 million. Not exactly, but close. And the denominator, well, I'll have that 1,000 cubed. This will be 1 billion. Already we're somewhere around a 0.003. If I throw an extra 0 in here, this next one will be really, really close to 0.003. If I throw another 0 in here for my x, the next one will be 0.00003. And again, all those are approximations. But the denominator is going to get big a lot faster than the numerator because it has the higher power. So if you see that case, you can automatically write down 0. If you see either of those 2 cases on the final exam, and you understand the concept, Both of those should take about 2 seconds. I could look at this one and say it's 0. I could have looked at the previous one, realized that the lead coefficients were even. I'm sorry, the powers were even, and I go by the ratio of the lead coefficients. Based on the graph of problem 1, find all values where x is not continuous. Oh, I talked about that already, didn't I? It was not continuous at -1. There's a big jump in the graph there. Not continuous at 1, not continuous at 2. Find the intervals where each function is continuous. Well, I look at problem B first, and I realize that that is strictly a polynomial. I don't even really care exactly what the graph is. A polynomial is a function that's always continuous, so who knows what it looks like. There's never a place where that one stops and starts and picks up again. In the second one, however, I have the typical rational function. And rational functions aren't defined whenever the denominator is 0. So I'm going to consider the cases where the denominator is 0. I can plug in any other number in the world on that rational function. I mean, it doesn't matter what number I plug in, as long as the denominator isn't 0. So I'm going to try to find when is x squared minus 7x plus 12 equal to 0. I think this is factorable, x minus 3, x minus 4, sure enough. So it's not going to be at x equal 3 and at x equal 4. Those will be the two cases where the function is not continuous. So where is this one continuous? Well, all numbers before 3, all numbers between 3 and 4, and all numbers bigger than 4. So those are the two values that this function cannot have. If I tried to plug in x equal 3, I would get -6 over 0. That's not a number. If I tried to plug in x equal 4, I'd get -3 over 0. That is not a number. Those are two places where I have vertical asymptotes, and the function's graph would have to stop and start and pick up again. Given the function f of x that's differentiable and continuous at 5, find each of the following. Okay, it's differentiable at 5 and it's continuous at 5. Differentiable means the derivative exists. Continuous means I don't have to stop and start. Let's see, I don't remember where this problem is going. Oh, find the slope of the secant line. Okay, so over here, someplace at 5. And then I'm plugging in another point, which is 5 plus h. So maybe I have a point here, maybe I have a point there. This would be f of 5. This would be f of 5 plus h, whatever y value I get back when I plug those in. Now, I don't know I have no idea if this is what the graph looks like, but they could be connected with some sort of a curve. Demonstration purposes only on this. The slope of the secant line is the slope of the line that exactly connects those two. It's not the slope of the graph at that point. It's not the slope of the tangent line, but it's the slope of the line that connects those two. So it's change in y over change of x. It's f of 5 plus h minus f of 5 over 5 plus h minus 5. It's the old change in y over change in x. Everything in the derivative part of this class dealt with the fact that the slope formula is the slope formula. So there it is written out in a little more precise terms. So there would be the slope of the secant line. What modifications would you need to find the slope of the tangent line at 5? Well, we want this interval between 5 and 5 plus h to be as small as possible. So if we keep moving this 5 plus h closer and closer, we get a closer idea to what the actual slope is. So if we take the limit here as h goes to 0 of this, that's the formula for the first derivative, and that will at 5, and that'll also give you what the slope is of the tangent line. Two cameras are 1,000 meters apart. Car passes the first camera at 12:54:45. The same car passes the second camera 45 seconds later. Right? Yeah. So it goes 1,000 miles in 45 seconds. That's 0.75 of a minute. Kilometers minutes. So I already converted that seconds to minutes. 45 seconds is 3/4 of a minute. Let's do that division if we could. Divided by 4 3/4, that'd be 1,000 times 4/3. Checking my work real quickly. I changed this problem a little bit from last semester. Let me make sure I did it right. Okay, so it looks like it's about that many kilometers per minute. Wait a minute. Okay, wait a minute. 1,000 meters apart. Okay. That was going awfully darn fast there for a second. Okay. It's that many meters per minute. All right. So now let's get it back to kilometers per hour. Man, I was flying there. I didn't think I screwed it up that bad. It's that many meters per minute. So let's see, how many kilometers would that be? That's 1,000. So it'd be 1.333 ... kilometers per minute. And if I multiply that by 60 minutes in an hour, I think that comes out to be 80, doesn't it? Yep. 80 kilometers per hour. All right, can the average speed of the car in that time period be determined? Heck no. All we know is there's camera 1, there's camera 2. It got there in that 45 seconds. We don't know how fast it was going here or how fast it was going at the end. All we know is the average speed. There's all sorts of different ways, different speeds you could have passed this camera and got to that camera 45 seconds later. Could have started slow, hit the foot feed, accelerated, gone a lot faster at the end. Could have thought that maybe this was a speed trap, maybe you're going 120 in the beginning, hit the brakes, slow down. There's no way we can know what that instantaneous speed is. We do know the average speed over that interval, but not the instantaneous. If the speed limit is 65, can we determine that the car was ever speeding? Oh yeah. No matter how you get from here to here, if your average speed is 80, either you're slower in the beginning and faster at the end, or vice versa. At some point, we don't know precisely when, but I can guarantee that at some point between the first camera and the second camera, you were going exactly 80. Maybe you're on cruise control, did 80 the whole way. That's possible. But there's all sorts of different scenarios getting from here to here. All of them have you going 80 for at least sometime in the interval. If the speed limit was 90, can we determine the car was never speeding? Heck no. All we know is the average speed. That 45 seconds, that 1,000 meters between them gave the car a lot of ample opportunity to speed up or slow down. Sketch the graph of x squared. All right. X squared is a nice function to illustrate a lot of calculus ideas. It's got curvature to it. And I'm gonna, probably graph paper might be handy on this one. I'm gonna steepen that up a little bit so that the scale looks a little better. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 0, 1, 1, 2, 4, 3, 9. And then I'm going to do my best to draw this. And if there's one of these on the final exam, you'll have the perfect drawing up there. Find the formula that gives the slope of the graph. Well, the slope of the graph is determined by, hang on a second. Here's my doorstop. Well, that didn't work. Slope of the line is determined by the derivative. F prime of x is 2x. That gives you the slope at every point. If we plug in 0, we get a slope of 0. If we plug in 1, we get a slope of 2. If we plug in -1, we get a slope of -1. Draw the tangent line at x equals -2. So if I calculate f prime of -2, that's the slope at -2. That's 2 times -2. That's -4. So here's how I'm going to draw the graph of the tangent line. First off, I'm going to locate the point on the graph. Here it is, 2, 2, 4, right? So I want the graph at x equal to -2. So there's order pair -2, 4. Now I'm going to use the fact that the slope is -4 to come up with a second point. I go down 4 points, 1, 2, 3, 4, over 1. There's the next one. Grab out my tangent or my ID and draw that tangent line right there. Now, if I had a perfectly well-drawn parabola, that graph would have just kissed that at that one point and would have moved away. That would have been the tangent line. So what gives us the slope of the tangent line? The derivative does. On to page 2, number 10. Find and simplify the average rate of change. This isn't the instantaneous rate of change. This is the average rate of change. This is finding the slope of the secant line, if you want to think of it in those terms. So here's the formula: f of x plus h minus f of x over h. It's again the change in y over the change in x. It's the slope formula. So let's calculate f of x plus h for the first one. 5 minus 2 times x plus h. You might want to recall back to the 4-step method. The average rate of change is the first 3 steps. The 4th step was to find the limit as h went to 0. So we're going to do the first 3 steps here. So starting step 1, you calculate f of x plus h. This part right there, simplified, is 5 minus 2x minus 2h. Okay. Step 2, you subtract the original from that. So you take this 5 minus 2x minus 2h, and from that you subtract the original function, which was 5 minus 2x. Now, if you do this carefully, you should see that this is a 5 and that's a minus 5, and they cancel. And here's a minus 2x minus a negative 2x distributed through. Those cancel as well. Excuse me. Messed that up. So distributing this, so yeah, I had it right there and I copied it wrong. So the 5 minus 5 goes away. The minus 2x minus a negative 2x go away. And you're just left with negative 2h. Now in step 3, you take that result, which is now the numerator, f of x plus h minus f of x. Step 3, you take that and divide it by h, and you get minus 2. What does that tell you? That tells you that the slope for any point on the graph, f of x equals 5 minus 2x, that tells you the slope is always equal to minus 2, regardless. Notice there's no x anyplace in here. The slope is always minus 2. Okay. Now, if I go on, and I'm going to do problem 10 and problem 11 right alongside each other. So here's the answer to problem 11, part A. I take the limit as h approaches 0 of my function negative 2, and I get negative 2. So here's 11, part A. 10 part A takes me through the average rate of change, which is just this formula. Problem 11 has the instantaneous rate of change. I take the limit of what I had before. So the first 3 steps, that's the average rate of change. There's no limit involved. Like the average speed, we didn't know exactly the precise speed at any one time of that car in the problem a couple seconds ago. We calculated the average speed. As you shrink the time interval down, you get closer and closer to the actual speed. Okay, on to problem B. F of x is 25. Well, if f of x is 25, f of everything is 25. F of x plus h is also 25. Take 25 minus 25 over h. That's 0 over h, which is 0. 0 divided by anything is 0. So there's the first three steps. That's your answer to 10b. Now you take the limit as h approaches 0 of 0, and you get 0. The slope of that line, y equals 25. Think back, y equals 25 is that line right there. The derivative tells us the slope. The slope is 0. On to part C. Part C, we have the function f of x is x cubed. Again, I'm going to start with a graph here. Here's the graph of x cubed. So this one is going to have a positive slope all the way through, except for right there at 0. So let's see what the average rate of change is. Let's calculate f of x plus h first. That would be x plus h cubed. Well, those two we've multiplied together a number of times in this class. It might take a little work to recover exactly how I'm doing that, but there it is. Oh, sorry, Sarah. 7b and 7c would be no. Yes, that is correct. (7d). Yep, we cannot determine whether the car was ever speeding. Yep. And by the way, if you're unsure after I go through this and you want to have a look at it again, I do have the answer keys for this whole activity set. They're there also on Blackboard. All right, so now we're going to have to multiply this together. I'm going to take x times each of those first. X times x squared is x cubed, plus x times that term gives me a 2x squared h, plus x times that term is x h squared. Okay. Now I'm going to take h times each of these terms. The first one will be an x squared h, plus that times that will be a 2xh squared. And get rid of that arrow a little bit, and then finally plus h cubed. And I'd like to simplify this if I can, and I can. Those two are like terms. Those two are like terms. X cubed, 3x squared h, 3xh squared, and h cubed. So I've just done the first of the three steps. Now I'm going to do the second. I'm going to take this, subtract x cubed. So there's f of x plus h minus f of x. When I do that subtraction, notice those cancel. I'm left with this. Now I divide that by h. One more time, notice that there's an h in each of the terms in the numerator and also in the denominator. So I can cancel that, cancel one of those, and cancel one of those as well. So here's the average rate of change, 3x squared plus 3xh plus h squared. That's the formula for the average rate of change. Now I'm going to do part 11c. Now I'm going to find the instantaneous rate of change. I take the limit as h goes to 0 of this, and I get 3x squared. That tells me the graph, or tells me the slope of the graph at every point. If I plug in 0, I find the slope is 0. If I plug in x equals 1, at x equals 1, the slope is 3. If I plug in -1, I get 3 again. The slope at -1 is also 3. If I plug in x equals 2, I would get 12. The slope at 2 is 12, and so forth and so on. So parts 10 and 11 go hand in hand. One of them is the first one is the first three steps, and the second is the last step. The beautiful thing about this is, you end up with a derivative at the end. So then finally, let's move on to the last one. 3x minus 3x squared plus 8. There's our function. Let's calculate f of x plus h. 3x plus h's minus 3. And I'm going to just carry the FOIL part out already. It's x squared plus 2xh plus h squared. And you can go back and relearn that if you need. And then plus 8. And before you finish this step, make sure you have all the distribution done. 3x, 3h added together, minus 3x squared, minus 6xh, minus 3h squared, plus 8. There's f of x plus h. Now what we have to do after that is subtract the original from it. So we're going to subtract off. Now when I subtract this, I'm going to add the opposite terms. So I'm going to subtract off a 3x. I'm going to subtract off a negative 3x squared. I'm going to add a 3x squared. I'm going to subtract off an 8. And if I do that, what's left over is the second step. 3h minus 6xh minus 3h squared. So now I have the second step done. I've taken my original, calculated f of x plus h, subtracted my original from it. Now my third step is to take this function I just got and divide it by h. So 3h minus 6xh minus 3h squared over h. Notice an h is in each of the terms. That's 3 minus 6x minus 3h. There's your average rate of change for that problem, letter D, problem number 10. Now, if I go to 11D, I just take the limit as h goes to 0 of that thing right there, and I get 3 minus 6x. And I look back at that problem, that better be the derivative, right? I used the four-step method to find that. My original problem was 3x minus x squared. Uh-oh. Did I copy something down wrong? Oh, geez. I copied the problem wrong. No, no. Oh, no. All right. Let's go back to the start, I guess. That's the nice thing about this is I can check my work by making sure I have the derivative at the end. Okay. So back to the drawing board on this one. Missed a factor of 3. So here's my original, 3x minus x squared plus h. I'm going to calculate f of x plus h. 3x plus h minus x plus h squared plus 8. 3x plus 3h minus x squared plus 2x plus h. 2xh plus h squared plus h. 3x, 3h minus x squared minus 2xh minus h squared plus h. So there I have it, f of x plus h. Sorry about having that extra factor in there for a second. Now it's gone. First step done. Now we're going to subtract off from that f of x. We're going to subtract off 3x. We're going to subtract off a negative x squared, so we'll add x squared. We're going to subtract off an 8. Now carry it through. 3h minus 2xh minus h squared. Now I have f of x plus h minus f of x. I'll take that and divide it by h. 3h minus 2x squared, minus 2xh minus h squared over h. Cancel the h's, 3 minus 2x minus h. There's my answer to 10D. Now on to 11D. On 11D, I take the limit here as h goes to 0, and I'm left with 3 minus 2x, which is the derivative of my original function. Whew, much better. The instantaneous rate of change is also known as the derivative. So 12 is easy. If g prime of 3 is 2.5, what do we know about the graph? We know at x equal 3, the slope is 2.5. The slope of the tangent line is 2.5. Let's see, which of those do I need to go over? I'm going to leave problem 14a I'm hoping everyone can take the derivative of a polynomial by now. I haven't seen anything on any of your work that leads me to believe otherwise. On problem letter B, I would rewrite this as 25x to the minus 1 first. So there's my f function, f prime, keep the 25, bring down the power, keep the x, reduce the power by 1. Rewrite this as negative 25 over x squared. And as I recall back in the previous semesters, and by the way, it is all multiple choice, I did check. As I recall in previous semesters, usually the answer key did not include negative exponents. So we would have to write it like that. Problem C is again, bring the power down. 5x to the 2.4 is our original function. Keep the 5 as the constant multiplier. Bring down the power, keep the x, reduce the power by 1, and 5 times 2.4 I think is 12. 12x to the 1.4. Problem D has been a thorn in our side in this class and in previous classes as well. There is the product rule that you could use on this one, but if you did, you'd have a lot of simplification to do to get the answer that the answer key had. So what I want you to concentrate on this one and notice is that the denominator has a single term. It's known as a monomial. And if that's the case, I can break these three apart into three separate fractions if I wish. Do some simplification and then use the power rule. So this one is just 3. This one is just x. And this one is 8x to the minus 1. So I haven't taken a derivative yet. I've just rewritten this using the division property of a monomial. Now when I go take the derivative of a constant is 0, the derivative of negative x is negative 1. I'll bring down the power, keep the x, reduce the power by 1, negative 1 minus 8 over x squared. Problem letter E, power rule again. I remember early in the semester just drilling and over again what to do, how to write these numbers as the right powers. So my first step is to get these written in the right form so I can use the power rule. 5 square roots of x I would write this way. The next one I would rewrite as the coefficient 2/3 multiplied by x to the negative 1/2. Why negative? Because it's in the denominator. Why 1/2? Because it's a square root. Again, I've not done any derivatives yet. I've just changed the way these are written. So now let's use the power rule. 5 times 1/2. You can put that over 1 if you choose. Keep the x, reduce the power by 1. Minus 2/3 is a constant multiplier. Bring the power down. Keep the x, reduce the power by 1. 5/2, there's our coefficient, that's x to the negative 1/2. 5 over 2 square roots of x. Negative times negative is positive. The 2's cross cancel, plus 1 over 3 square roots of x cubed. Natural log of x, the derivative of that is 1 over x, easy enough. Letter G, the derivative of e to the x is e to the x, thank goodness. And then from this point forward, we have to use some of the more advanced rules. There's a product rule, a chain rule, got 3 versions of the chain rule and the quotient rule. On the final exam, there are none of those rule within a rule problems where you have a quotient rule hiding inside a power rule or something like that. So I think I have at least one example of each of those: chain rules, product rule, and quotient rule. Here's the first one that applies the chain rule. F of x is 12 e to the x squared minus 5x. The derivative rule for an exponential is 2. Well, first off, we'll keep the 12 because 12 is the constant multiplier. When you have e to a function of x, that thing never changes. That function comes down exactly the same. And then you're going to multiply it by the derivative of that power. So 12, 2x minus 5, e to the x squared minus 5x. So that's one of the two ways this answer could show up on the final. The other way, I think maybe someone would have multiplied the 12 through there and had 24x minus 60, e to the x squared minus 5x. Those would be the two anticipated solutions that I would get. All right, so there's our first chain rule. Here's our next chain rule in problem I. Now, you could look at problem I and say, well, Randy, you have a fraction there. Shouldn't we use the quotient rule? And my answer to that is, well, you could. It's just going to be a little more work. What I see on problem I is a fraction that doesn't have an x in the numerator. It just has a constant. So I'm going to rewrite this one as 6x squared plus 5x minus 40 to the negative 2 power. Now I'm going to use what's known as the modified power rule. The modified power rule follows the power rule. You bring the power down, you reduce the power by 1, but then you also must multiply by the derivative of the inside function. So I'm going to bring the power down. I'm going to keep the base exactly as it was before. I'm going to reduce the power by 1, and then I'm going to multiply by the derivative of that base function. Derivative of 6x squared plus 5x minus 40. So let's do that step next. Negative 2. Keep that thing exactly as it was to the minus 1. And then multiply that by 12x plus 5. Now let's put it together into a fraction again. This thing was to the negative 1 power, so that's going to go in the denominator. Now to the positive first power. And then in the numerator, it's either a minus 2 quantity, 12x plus 5, which is what I would prefer because it's factored, or maybe a negative 24x minus 10. But those would be the two appropriate answers for this problem. Okay. So there's the modified power rule. Bring the power down. Reduce the power by 1. Oh, holy crap, I screwed up. Reduce the power by 1. Whoopsie. Reduce the power by 1. Good thing I gave myself a talking to. Reduce the power by 1. Multiply by the derivative of the inside function. All right, on to letter J. Letter J, I noticed that there are two functions of x written one right on top of the other. The sign that's understood to be between those is a multiply sign. Here's the product rule. 5x to the x. So let's take the derivative of that. If you remember, the derivative for the product rule says the derivative of the first times the second plus the first times the derivative of the second, although you could interchange those, it wouldn't make a bit of difference. So the derivative of 5x is 5, copy down the e to the x. F of x is 5x, multiplied by the derivative of that, which is e to the x. So there's one of the two ways that this answer could be seen. The other way is in factored form. Notice both of these have a 5 and an e to the x in them. 1 plus x would be the other factor. And always check your work. Make sure when you distribute through, you get exactly what you had before. So there's the product rule. Looking on to letter K, I see the quotient rule. This is different from problem H, or problem I. In problem I, we didn't have an x in the numerator. We just had a constant. So I didn't need necessarily to use the quotient rule. On this one, I'm pretty well stuck with it. Some people I've noticed have experimented with rewriting this in a different form and using the product rule. And you could, but there's going to be a penalty to pay, I think. Okay, here's what some people do. I noticed this on maybe 5% of the papers back when we did problems like this. I think was on test 2. Rewrite it like this and then use the product rule. The problem is the answer that you get using the product rule isn't going to align with the way that this one is written using the quotient rule without quite a bit of advanced algebra. So it takes algebra to get it through to look like one of those 5 answers on the answer key. So my suggestion is you just do this using the quotient rule. Quotient rule says you take the denominator and square it. You bring the denominator up. You multiply it by the derivative of the numerator. Stick a minus sign in between there. Derivative of the denominator times the numerator. So there's our sort of roadmap to getting us where we need to go. So now we're going to work with the numerator and get that as pretty as possible. So this is e to the x minus 5 in parentheses times 3 e to the x minus the derivative of this is simply e to the x because 5 is subtracted off times 3 e to the x. And for now, I'm going to ignore the denominator. I don't want to waste a whole bunch of time to keep writing this over. I'll bring the denominator back in at the end. So I'm just working with the numerator now. The derivative of that is that. The derivative of that is that. Now let's put things together and see if we can make this simplified. But when I have two like bases multiplied together, I add the exponents. So this is 3e to the 2x minus 15e to the x. So I distributed that through minus, and look at this. This is again 3e to the 2x. Notice I add this on and subtract it off later, and they cancel. So negative 15e over that whole thing squared, my original denominator squared, e to the x minus 5. All right, so product rule, quotient rule. The last several explore what to do if we have a log of a function. So the first one says, okay, do you remember the natural log chain rule? The natural log chain rule, to me, was the easiest of all of them. If you had y as the natural log of a function of x, when you go to find the derivative, you write that exact function in the denominator and its derivative in the numerator. So let's see if we can make that law work on really on all four of the next problems. So starting with the first one, the natural log of 4x squared plus 3x. I'm going to take that function that follows the log, put it in the denominator, and put its derivative in the numerator, a nice easy polynomial, 8x plus 3. I'm going to look for like terms. There's not a 3 in all of these. There's not an x in all of those. There's not a 4 in all of those. That problem is as simplified as it can possibly be. So that was the straightforward application of the log part of the chain rule. Now, on the rest of these problems, we're going to use some law of logs to help us get there. Notice we have 7x e to the problem similar to this a second ago. But if we have a log of two factors of x multiplied together, we're best off using a law of logs to rewrite those first. So I'm going to rewrite this one as the natural log of 7x plus the natural log of e to the x. So as long as these two things are multiplied together, I can add those two separate logs. Now going on using the log rule. Put that in the denominator and its derivative in the numerator. That is 1 over x. I realize that natural log and e cancel each other out. That part right there, that's just x, and the derivative of x is 1. Now, I could have used the chain rule part on here as well. I mean, I could have said, okay, let's put the e to the x in the bottom and its derivative in the top, and it's still e to the x, and e to the x over e to the x is still 1. So without recognizing that natural log and e cancel each other out, you still get there. Just apply the natural log rule. On to problem n. Problem n, we have a different law of logs to use. In this case, we have a power, a log of something to a power. So I'm going to do the first step for you. I'm not going to rewrite the problem. I'm going to do the first step for you. If you have a log to a power, you can bring that power down and make it just be a coefficient. So we have that coefficient of 2 that has to carry down through the rest of the problem. So bring that down. We have the natural log of e to the 3x plus 6x. Okay. Now let's attack the derivative, f prime of x. 2 is the constant multiplier. We can write it as 2 over 1 if we wish. Now we're going to one more time use the chain rule for the logarithm. Write this down. And write the derivative of that in the numerator. Well, the derivative of e to the 3x has e to the 3x in it, and then you multiply by the derivative of that power. That's 3e to the 3x. The derivative of 6x is 6. If you now distribute this 2 through the set of parentheses, 6e to the 3x plus 12 over e to the 3x plus 6x. Notice I have 4 terms, and notice there's not a common factor in all 4 of those terms. There's a 6 that falls in 3 of those, but no 6 there. There's no e to the x in the last 2. So that problem is as simple as it can get. And now finally, the last one on our long list of however many. I didn't use all the letters of the alphabet, but came close. The last one of the straightforward derivatives. I'm going to rewrite this one using a law of logs. If I have 2 logs, one divided by the other, I can separate those out and write the first one minus the second one. So there I did it. I didn't rewrite the problem. I just did the first step. That was F. Now I'm ready to use the log rule. That goes in the denominator, its derivative in the numerator. That goes in the denominator, its derivative in the numerator. Now we're not asking you to get a common denominator and add these. If there's one like this that appears on the final, the answer will look like, well, something like that. Here we have a common factor of 3 that would cancel. 1 over x, 5, oops, no 5 there. So we are done. Okay, problem 15 for parts A, B, H, I, J, and L. Find the values of x where the tangent line is horizontal. The tangent line horizontal gives us a lot of options here. It's usually where a function is at a max or at a min level. That's why we concentrated on that pretty heavily. So let's go back and see if we can do those. All right. So I'm going to write up the derivative on these and see where we can go. The derivative on the first one is 75 minus 3x squared. Set that equal to 0 and solve. Well, we have a quadratic equation. 75 is 3x squared. 25 is x squared. X is either plus or minus 5. Plus 5 in there, throw minus 5 in there, it doesn't matter. That derivative is 0. On the second problem, we found the derivative. The derivative on part B was negative 25 over x squared. I'm asking when that is 0. Well, a fraction is equal to 0 only when the numerator is 0, and this numerator is stuck being 25, so that one will never have a slope of 0. Problem letter H. Doggone it, I erased all these, huh? Right, problem number H. I'll go through this mentally and write the answer up here. Let's see, that would have been 12 times 2x minus 5 times e to the x squared minus 5x. Set that equal to 0 and solve. The nice thing about the product rules, you're left with factors. Or I'm sorry, the chain rules, you're left with factors. And we set each of these factors equal to 0. Well, 12 can't be 0, it's stuck being 12. This can be 0 when x is 5 halves. E to a power is never 0. So there's only one place where this graph absolutely becomes horizontal, and that's at 5 halves. Let's see, which one was that? H? Yep, on to I. Oh, I kind of remember I now. I was the one who screwed up a second ago. It should have had negative 12x minus 10 over that cube. I'm going to check my mental math real quick. 12x plus 5 times a minus 2. Yep. Set that equal to 0 and solve. Well, just as I mentioned on the previous problem, the only time a fraction is 0 is when the numerator is 0. When it's negative 12x minus 10 equal to 0. 2 steps of algebra later, you get what? Negative 5/6, I guess. Okay. J, was that J? Nope. Here's letter J. We had letter J just a second ago. It was 5x e to the x plus 5 e to the x. I factored out of 5 e to the x. And I believe when I had it done before, it was just 1 plus x was 0. Now I'm going to ask when are each of these factors 0. 5 is never 0. E to the x is never 0. That's equal to 0 when x is negative 1. And then finally, problem L. Problem L, I'll recreate the derivative as quickly as I can. H of JK L, 4x squared plus 3x in the denominator, 8x plus 3 in the numerator. For one last time, a fraction is equal to 0 when the numerator is equal to 0. Set that equal to 0 and find that x is negative 3/8. Okay, done with problem 15. On to problem 16. This is one taken directly from our one of our activities. I've changed the numbers up maybe a little bit. No, exactly the same. Find the profit earned to the nearest dollar for the sale of 10 balloons each week. So here's where we're starting in. We've got the rules of derivatives done. Now we're starting in on marginal analysis. I made this review guide sort of go chronologically with what we covered in class. So what we'll do is just calculate P of 10, plug it in, and figure out what it is. I'll let you do that on your own. It looks like it's got to be, gosh, 12,500. Looks like it's got to be somewhere around 13 grand. That's certainly a calculator exercise. Based on the graph, does it make sense to increase manufacturing beyond 10? Well, sure. That's our profit function. We're here at 10. If we produce, what, closer to 15 or so, we're going to be making more profit. Another reason is because the function is increasing at 10. By examining the graph, what can we determine about the value of the first derivative? Well, at 10, the function is still increasing, so the first derivative must be positive. Using the straight edge, draw the tangent. This is something that this class did exceedingly well on. Understood tangents. I think maybe because I covered that in the algebra review, if I'm not mistaken. So there's a tangent right there. It just hits right there at 10 and then kisses the graph and bounces away. By examining the graph, what can we determine about the second derivative at 10? Well, second derivative tells us about concavity. This is concave down. And since it's concave down, we know the second derivative must be negative. Using calculus, find the slope of the graph at x equal 10. So that would be p prime at 10. Let's do p prime first. I think I can use the power rule all the way through. I can. The derivative of negative 2,500 is 0. The negative 2,000, derivative of 2,000x is 2,000. And the derivative of 15x to the 2.5. Let me do 15 times 2.5. 37.5. Reduce the power by 1. There's the derivative. Calculate whatever that is when you plug in 10. Okay. And I don't have the number for that, and I don't want to bother with it. But it's got to come out positive, right? The slope is positive. Otherwise, you mess someplace up in the problem, or I messed it up. I write the marginal profit function. The marginal profit function is the derivative. So it is right there. Without any further calculations, write the value of the marginal profit function. Well, whatever we got here, it's the same thing. It shows us how quickly the profit is increasing as we manufacture more balloons. Without any calculations, will the value of the marginal profit function be a positive, negative, or zero at the production level of 20? Over here at 20, the function is heading downhill. It's a decreasing function, so the first derivative will be negative because the function is decreasing. Use calculus to find the maximum profit. Okay, maximum profit is right there at the crest of the hill. At the crest of the hill, the first derivative is equal to 0. So I will take this and set it equal to 0. I might need a calculation here. So someone with a calculator, help me out here. I don't have the 1.5 power button on my calculator. I'm going to set that equal to 0 and solve. So I have 2,000 equals 37.5 x to the 1.5. X to the 1.5 is equal to 2,000, divided by 37.5, 53.33. And this is x to the 1.5 power. To solve this one, what we'll do is take this to the reciprocal of 1.5. So either 1 over 1.5, if you want to do that, or you could realize that this is 3/2 and take both sides to the 2/3 power. So someone with a calculator, help me out with that one. I'll move my calculator button out of the way for a second so I can see. Can't get it to slide. Oh well. Oh, hang on. I can do that in the browse bar. Like 14.6, that looks 14.16. Yep, about 14.17 balloons. That, of course, isn't the maximum profit. That's where the maximum profit shows up. So plug that number back into the profit function, and you will find the maximum profit. Yep, 14.17. Thanks, John. Appreciate it. Plug that back into the profit function. If someone wants to do that, tell me that number. I can look at the graph and say, it's got to be right at $14,000 or so. But I'll let someone out there in YouTube land plug that into the original function. Or I guess you could look at the answer key too. Write the average profit function. Well, the average profit function is the total number of dollars we make on X balloons divided by the number of balloons we make, which is X. So we take the original function and divide it by X. I'm not sure how the answer key is going to be on a problem like this. I'll give you both possible answers. So either you take the original function and divide it by X and leave it in that fraction, or you individually divide each of those by X and leave it in that. 2 pages done. On to page 3. So problem 17 is one we haven't talked about much in this class. It's a really easy concept. Where does a function not have a derivative? Well, if you can't tell what the slope is, it doesn't have a derivative. That's basically what it comes down to. Or if the function isn't defined. So I'm going to put up all the points where I'm going to draw the whole graph, I guess. I'm going to run a little low on ink so I got a better pen here. If I don't, I might have to run downstairs and open one more. So I have a graph that comes to a point. Oh, nice. We have a graph that has an open circle. We have a graph that goes straight up momentarily. We have a graph that has a discontinuity. And it goes on. Okay. There's no way we can draw a tangent at this point. That point is known as a cusp. It's a quick change in direction, not the nice, smooth, flowy thing we typically have. The derivative does not exist at letter A. At letter B, the whole function doesn't exist, so the derivative can't exist at B either. At letter C, and this one's sort of hard to tell, and it'll be really clear on the final. But at letter C, this graph goes straight up, so the slope is undefined on a straight up and down graph. So it's undefined, the slope is undefined at C, so there is no derivative. And then of course at D, where the function breaks, there's no way we're going to draw a tangent line there at D, is there? If there's a discontinuity, there's no derivative either. So there we have it. A, B, C, and D, things to look for. Cusps, places where the function is undefined, places where the function momentarily goes straight up and down, and any place you have a discontinuity. So look at those carefully. When this one comes up on the final exam, it should be fairly obvious if you understand just those four things. Cusp, undefined spot, place where it goes straight up, or a place where the function is discontinuous. On to 18. Suppose that price-demand function is given by that where the x is demand level, the cost to produce. Find the maximum profit. Okay, easy enough. So we're given a price-quantity function. So the price-quantity function is 2,500 minus 35x. X is the number of units demanded. This is the price. So this is the price. X is the number of units demanded. This is how many, this is the dollars we're going to get per unit sold, and X is the number of units sold. So the revenue is going to be 2,500 minus 35x times X. Price per unit times the number of units sold. 2,500x minus 35x squared. That's the amount of money we have coming in, depending on how many units we produce. The cost function is 4,500 plus 10x, and the profit is going to be the revenue minus the cost. So 2,500x minus 35x squared minus the cost function. Do that right? Yep, that's good. Simplify the profit function. 2,500x minus 10x. 2,490x. No like terms there. Minus 4,500. Okay. Find the derivative. 2,490 minus 70x. Set that derivative equal to 0. And by the way, I can look at this function and realize it's an upside down parabola. So I'm sure that when I set this equal to 0, I'll have the maximum point. I could take the second derivative and realize that that's a negative sign, which tells me the graph is always concave down. But if I set this equal to 0 and solve, I find x is 2,490 divided by 70. And whatever that number is, that tells us how many we should produce. So take this number, whatever it comes out to be. I guess I can calculate that as well, can't I? $249 divided by 7. That's 35.6 about. That's the number of units we should manufacture. Plug that back in the profit function, and that will give us the maximum profit. Problem 19, parts A and B deal with Newton's law of cooling. First function has nothing to do with calculus. The second function has everything to do with calculus. What was the temperature of the center of the panel design 15 minutes after it was removed? Well, whatever 70 plus 235 e to the negative 0.025 times 15 happens to be. Let me check my units here. Number of minutes. He's the number of minutes, so you'll figure that one out. And then find t prime of 15. T prime of 15. Okay, here's my temperature. My derivative would be 235 times negative 0.025 e to the negative 0.025 t. Do that calculation real quick. 0.025 times 235, 5.875. So negative 5.875 e to the negative 0.025 t, and we want to evaluate that at 15 minutes. Evaluated at t equal to 15. That'll be the number we're going to get, and it's got to be negative. The temperature's coming down after it's taken out of the oven. So whatever this number comes out to be, I'll let you fill in the details here, but here's the sentence I would write. 15 minutes after removal, temp was, since this comes out negative, was decreasing at a rate of whatever number you got here, degrees Fahrenheit per minute. The original function tells us what the temperature is. The derivative tells us how quickly that function is changing value. Problem 20, the number of PIs is given there. Okay, find the relative rate of change. And watch how my sentence on problem 20b is going to fall exactly like it did on 19b, with one exception right at the very end. Relative rate of change function is the derivative over the original. So the derivative would be 6.8t divided by 50 plus 34 t to the 0.2. This would be to the negative 0.8. So this function is copied down directly from the number of political independents. The derivative of this goes on top. Derivative of 50 is 0. Here we bring down the power, 6.8. Keep the t, reduce the power by 1. So we want to figure out what the rate of change was in 2016, and t is the number of years since 2004. So I guess 3 election cycles later, we plug in t equals 12. So we're going to evaluate this at t equals 12. And I don't have the answer key ready for this one, but let me, I probably better look at the answer key just so I don't steer you wrong as far as how we're going to answer this question. Let me see if I can find it on my Word file here. Oh, I could find it online too, couldn't I? Let's see. 20B. 20b, we get, when we plug that value in, we get a 0.0088. Okay. Yep. At least that's what the answer key said, and I'm believing it since I did this answer key a couple of times. So now we're going to come up with the sentence. Now the sentence here is going to mirror what it would with a derivative. Our original function gave us the number of political independents. So the derivative is going to tell us whether that number is going up or down. In 2016, the number of political independents is, since that's positive, it is increasing at a rate of. Now here's where this is different from the straightforward derivative. The straightforward derivative would tell you how the number of PIs is changing per year. This is going to give us a percentage change, 0.88% per year. So not quite 1% per year, but close to it. And that's a fairly significant change. 21, the value of the automobile is given there. I've written out those answers in the answer key for 21, both A and B. I'm hoping that you can follow those answers. Marginal analysis, I thought went pretty well way back when. And I've just done 3 answers on marginal analysis, so I don't want to write them out. I guess I could recite them to you if you wanted me to. I'll do that. 5.5 years after Sal purchased the automobile, the value was $6,500. 7 years after Sal, here's part B, 7 years after Sal purchased the automobile, the value was decreasing at a rate of $325 per year. On to 22. The first derivative is positive on which intervals? Well, if the first derivative is positive, that means the function is increasing. So I'm looking where it's increasing for part A. Negative infinity to -1, and then it increases again starting at 5 and goes to infinity. So I'm using what I'm given here, and I'm saying, okay, what does that mean? So what I'm writing here is what result do I get? Part B, when is the first derivative negative? If the first derivative is negative, then the function is decreasing. Where is it decreasing? Well, those places where it isn't flat or increasing, from -1 over to 5. So again, looking at the graph, I'm plugging in the x values just to be perfectly clear here. So where am I getting this -1 and 5? There's the -1. There's the 5. Increasing till I get to -1, increasing from 5 to infinity, decreasing from -1 to 5. Part C. The first derivative is undefined for what values? Well, this function is never undefined. The derivative is never undefined. There's no cusp. There's no place where it goes straight up and down. There's no discontinuity. So that never happens. That's part D. I'm on part C. The first derivative is 0. Yeah, it's 0 right here where it goes flat. It's 0 right here. So here's where the graph is flat. X equals -1. And x equals 5. Part D, never. Part E, the second derivative is positive on what intervals? Well, if the second derivative is positive, that means we are looking for the place where this is concave up. There's concave down, there's concave up. I'm guessing I'm going to split the difference between -1 and 5. I guess that would be at x equal to 2. So probably, as far as I can tell from this graph anyway, from 2 to infinity. And the one that's like this on the exam, I mean, there's not going to be any doubt. Okay. The second derivative is negative on what intervals? Well, here we're looking for concave down. Concave down is that region of the graph from -infinity to +2. Second derivative is 0. That's where the graph is perfectly straight. That's where it stops being concave one way and starts being concave the other. That's at x equal to 2. So critical points at -1 and 5. This is known as an inflection point right there at 2. What can we say? Here's part H. What can we say about the second derivative at 5? Well, the second derivative determines concavity. That's concave up. So I am sure that at 5, the second derivative is positive value. It's bigger than 0. What can we say about the first derivative at 2? Well, at 2, the function is decreasing, so I can tell that that is a negative value. G, H, I. Positive, negative. Hour and a half. Hey, just as I planned. Hour and a half, and we're through the first 2 pages. Nice. Do an hour and a half tomorrow. That'll probably get us through the rest of it. I'll spend a little time later today bookmarking this video so that people who have a question or two along the way, or if you have a question or two along the way, you're working through again with something you didn't pick up, well, you don't have to wade through hours and hours, minutes and minutes, 90 minutes trying to find it. Take a little break now. I should have that done by 5 tonight, however. So there we have it, the first 2 pages. Come do the second 2 pages starting tomorrow at 1. I look forward to connecting with some of you then. If you do have individual questions on any of the work I've done so far, send me an email. We can either correspond via email or we can do some sort of a video chat. Let me know. Otherwise, I'll look forward to presenting again here tomorrow.